Hello, how's it going? Who had some gin? I still have mine too, so cheers. I am happy to be here again with Matt, and we're going to talk about Jtagsploitation because it's a really cool conglomeration of words. Basically 5 wires to JTAG, and we'll show you 5 ways to get root on a JTAG system. This is me. I'm Joe FitzPatrick. I'm an electrical engineer by background, and the security part just kind of followed on. I did kind of a lot of focus on computer science and InfoSec, which is where I got interested in this stuff. I spent 10 years doing all sorts of stuff on hardware, including silicon debug and pen testing of desktop and server CPUs, so hardware hands-on pen testing of that stuff. For the past 2.5 to 3 years, I've started doing a lot of hardware security training. I taught software exploitation via hardware exploits over the past year, and I'm working on a new class, Applied Physical Attacks on x86 Systems. Anybody who's interested in taking that, it's going to be at hardware.io next month in The Hague, and also in Seattle, in the USA, in December. I think that's all I do.
Hi, I'm Matt. My background is in hardware design, so I've spent a lot of years designing and implementing and now misusing hardware test and debug features, so all the fun things that silicon manufacturers put into a device so they're sure it works before they sell it to you. So I'm currently employed doing hardware and firmware pen testing.
So Jtagsploitation. You kind of know what this part means, right? Exploitation, kind of exploitation. That's the stuff that exploit people do and all those merchants of death and stuff. But what's JTAG? Who here has used JTAG before? OK. Who here knows what JTAG is? Who here wants to know what JTAG is? OK. Joint Test Action Group. OK. Who's here's a joint tester? Any joint testers in the room? No, just checking. Joint Test Action Group was actually a group that formed to create a standard that would allow silicon test to be a lot easier. So the standard is IEEE standard 1149.1, the IEEE standard test access port and boundary scan architecture. So anybody who was curious about what JTAG is, you've got that answer now. Not really. So we'll kind of go into the lower levels of what JTAG is to give you a better idea. Is basically it comes down to this is a way to debug hardware. And when we say debug hardware, we're talking about silicon and boards. And in the recent past, well, not that recent, 20 years plus, we've also added the ability to do software debug of silicon chips over JTAG. So we'll talk about how we get there. Do you want to start? Or?
Yeah, so the only other point I wanted to mention is that this stuff is really in there primarily for the manufacturers. It's not there for software people. It's there for the people building the chips and building the systems. So if you want a laptop that works, they use JTAG to make sure everything's soldered up correctly and connected correctly and making sure the chips are working properly in the first place. So the background is that's why it's all in there, right? Because the hardware people need it to make sure stuff works because you really don't want to buy a system that doesn't boot up when they give it to you.
So who's seen this 7-layer diagram before, over and over again? Yeah, everyone has. So we figured since everybody's seen that, we'll just kind of base what our description is off of that. So when we look at the JTAG model and we go into similar layers, when we have a physical layer, what we're talking about is a couple pins. So we have 5 wires, TDI, TDO, TMS, TCK, and T-reset. But T-reset is optional, right? If we have a bunch of chips on a board, we can hook them all up. And our tap data in, TDI, data in, goes in one chip and strings around through all sorts of neat stuff inside that chip, then connects TDO to the TDI of the next chip, OI, and then back out to the other end. Inside, we've got this mode select, TMS, and our tap clock. Those control what each of these things are doing with the data that gets shifted in and out. So what it comes down to is we have 5 wires, and we can hook up 1, 2, 10, 500 chips on a board and have this very simple 5-wire interface to debug everything that's happening in the system. Sure.
So there's a really simple protocol. Well, it's a pretty simple protocol they use to control what's actually going on. The main things you're looking at when you're using JTAG are the data in and the data out, and the clock and the mode select are just sort of there to let you get through the states and access the data in the registers. So if you go on to the next slide, this is the tap FSM. There's a whole bunch of extra states in there. Most of them are not interesting and are there strictly to support the limitations of either devices being tested or the devices doing the test. So there's some pause states and there's some early exits and other things that are there to make the software and the hardware a little simpler. But if you go to the next one, you can really simplify because you're really doing one of two things, right? You're either writing an instruction or you're reading or writing one of the data registers. And that's really about it. So if you go on the next level here, right, so the two kinds of registers are the instruction register and the data register. So this is sort of an abstracted, you'll see several different pictures. This is my favorite one of how to sort of explain what's going on. The instruction register really just lets you select one of the data registers, and then the data register is just, it's a register. It's a serial register. You put data, shift bits into it, bits come out of it. And almost all of them are manufacturer defined. So it's whatever the developer of the chip put in there that they thought they would need in order to do debug of this device.
When we use the word register, we're referring to a hardware register. So we're not talking about R0 through R15. We're not talking about AX, BX, CX, DX. Those are the instruction set registers. There's software registers and general purpose registers that you use to do stuff. From a hardware perspective, when we say register, we mean bits of storage scattered throughout the chip. They could be accessible from software. They could have a name like MSR or something like that. But it's also very likely that they're just a hardware value that's somewhere in the chip stored in a flip-flop, a little electrical circuit that stores a bit. Could be 1 bit, could be 10 bits, could be 372 bits.
1,000 something.
Yeah. So that's what we mean when we say register. So each of these registers, these data registers, have something and they have a specific purpose. We'll talk about some of these purposes in just a moment.
Go for it.
So on top of that, we have this ability to talk about IRs and DRs, and that's really our interface. We have an instruction register, sometimes they're called opcodes, and the data register, which is where we throw the data we want it to operate on. If we look, this is from the specification for JTAG, which is the JTAG spec for most MIPS processors. What they say to do is, okay, you have a code, which is the actual value of the ID code, of the instruction register. If your instruction register is all zeros, right, free for other use. If it's a 0x01, so if that's our IR, we put 0x01 into our instruction register, it's going to select this ID code register. The ID code register is actually a product identification register, so a manufacturer can put a couple bits in there that represent a manufacturer ID, and then a hardware ID and a hardware version number. But as we go down, we see there's a bunch of different things. There's address and data and control. There's some boot settings. So these are all the lowest level things we might need to use to figure out what's going on a system, figure out what a part is connected to, and access all that stuff. In between, we see all these free for other use areas. And what we're going to realize is we're looking at the MIPS standard for JTAG. So if you have a system on chip, one piece of silicon that has a MIPS processor, this is what MIPS says is going to be in JTAG. There could be other stuff in that chip that the manufacturer chooses to plug into these holes to have other features in JTAG as well. So this is just MIPS, though. x86, completely different. ARM, completely different. Different SoCs are going to be significantly different. You could have two SoCs that both use the same ARM core, and they'll have a couple instructions that are the same, a couple IRs and DRs that are the same to control the core itself. Everything else could be different entirely. x86, from one generation processor to the next, it could look completely different as well. So on top of that, maybe you guys recall from this stack that we have this session and presentation layer that JTAG is sessionless. That doesn't matter. No one actually uses the presentation. Wait, has anybody used a presentation later for any project they've done? Anyone at all? Okay. If anybody raised their hand, my second question would be, was it for an academic project? And the answer would be yes. So onward. Up to the application layer. So this is what can we actually do with JTAG? We talked about what's down below, but what is the purpose of all this? We have boundary scan, memory, and register access. Do you want to talk? Or?
No, go for it.
OK. So boundary scan, we saw this picture before. We have several chips on a board. We connect our data in, and we serially connect them all the way through. When we go into boundary scan mode, we're actually doing a very low-level hardware and silicon test. what we're doing is we're shifting bits through all the I/O pins of a chip. So if we had an 8-pin chip, an 8-pin chip, an 8-pin chip, what this boundary scan feature would let us do is let us set all of the outputs of those pins. And you can see right here, on our circuit board, we have a bunch of traces that go to yet another chip. By doing this, we can actually set the values that go out on those output lines, and we can either check with a logic analyzer or oscilloscope, or we could actually have another chip over here. These pins might be mapped over to this chip here, and we could be reading in at the same time. So we can see the connectivity. We know if we put a 1 here and we receive a 1 up here, we know that the chip is functioning, the output driver of the chip is functioning, the solder connection to the board is good, the trace is connected on the board, and then at the other end, the solder connection, the chip, and the input driver are all working properly. So this is silicon test, this is board test, this is boundary scan. So as an example, number 1, accessing non-volatile storage via boundary scan. So this is a Beaglebone Black. Who's played with one of these before? Anybody? If you flip it over and look at the bottom, there's these little gold pads. What you can do is you can solder a header on there, and that gives you JTAG access. So JTAG, as we said before, it has a whole bunch of things. This has an ARM core, so you could go debug this ARM core according to the ARM specification. But what we're interested in right now is boundary scan. So if we look at the CPU package, the subarctic AM3335X chip, and we look at the schematic, we see somewhere over here, these pins on the chip are mapped to the MMC pins, so the eMMC controller. Now, what I just mentioned about boundary scan is it gives us the ability to twiddle all those bits. So if this were inside some sort of plastic or epoxy case, if the traces are all on the bottom of the board, we can't actually reach them, or for some reason we don't want to desolder and remove a package, we still have the ability to access these pins by using boundary scan. Yeah, so what am I showing here? Pins, MMC pins. Oh, this is the bottom of the MMC chip itself. It's a BGA chip, meaning all the pins are little balls of solder on the bottom, so you can't actually access them from the board itself. You can also see there's a ton of pins, but we're only using about 10 of them, which is really nice about eMMC, because you don't have to worry about all those other pins. So we can use this program UR-JTAG. This is kind of the there's two tools for using JTAG, open source tools. There's UR-JTAG and there's OpenOCD. OpenOCD is on-chip debug. That's kind of the software person's JTAG tool. UR-JTAG is a lot lower level. This is more the hardware person's JTAG tool. This is what we use to poke around at boundary scan and other things. So we use this initbus command to initialize a bus on the selected part. Via BSR, via boundary scan register, it tells us we can use the boundary scan access to those pins. We define all these pins in a BSDL file, which tells us basically you have a string of 180 bits. These 180 bits map to these pins on your CPU, and it'll say, OK, bit 263 is going to be V7, 264 is R8, so on and so forth. What that means is you can use JTAG to construct a long string of bits that will shift in and go and set the output of all the relevant pins. So this would be our Beaglebone Black. This would be our eMMC. We shift in the pins we want. We wait a clock cycle. We shift in a new set of pins. We wait a clock cycle. Once we have the ability to access those pins, we can use a detect flash command to actually detect some of the parameters of the flash or memory device. We can read or write to that memory. So UR-JTAG has the ability to access several different types of flash and memory built into it because it knows you're going to have pin connectivity and pin control. So there's a lot of layers going on here. And remember, this is JTAG. This is 1 bit at a time for every pin on the whole chip. So it goes, and it goes, and it goes. So we've got a video demo. We actually decided that there was a lot of work involved in this one, and we should show it off first. And this is what paint drying looks like in HD. It takes a really long time to do something like this. But if we have no other way to get to a system, it's reasonable for us to sit there for a day or 2 days or a week and dump the entire contents of Flash this way, and then modify it and upload the contents of Flash. You have to be very patient with this, though. So we don't have patience.
Yeah, now this would have taken, on the Beaglebone, what did we decide, at least a week?
Yeah, at least a week.
I think that was actually optimistic when I figured that out.
That's if it worked the first time.
Yeah. The BSDL had, what, about 500 pins?
I think so. Yeah.
So you've got 500 bits you have to shift in for each phase of a clock cycle. Each half of a clock cycle. So in order to read things back out, and your JTAG adapter is running at 1 or 2 megahertz.
Yeah, and then you've got...
So your total actual bandwidth of reading stuff out is terrible.
Yeah, 1 megahertz divided by 500 pins minus the overhead times 8
minus
pins
the
that we're
overhead
actually
times
using.
however many clock cycles you need per
yeah.
byte. It's bad.
Long time. We didn't even want to do the math. It was so hard.
Yeah.
So onward. What's the point? What's the cons? It's really slow. You have to have the boundary scan or the BDSL file. It's really, really slow. Did I mention that? You have to actually emulate the whole flash interface protocol, which means you have to know some things about your flash. And once you're able to do that, it's still really slow. The good thing is you can access BGA pins without desoldering anything. It works regardless of whether your CPU actually has good JTAG support or fuses are locked. Basically, JTAG spec says that you've got to have this functionality, so as long as it's JTAG compliant, it's going to have the ability for you to do this to test your board. It works regardless of CPU functionality, and you can go visit a park, you can go out for a beer, you can take a week holiday while this works, and that's kind of an advantage for sometimes, right? It's like the hardware guy's version of my code's compiling. So.
All right, so one of the other big things that JTAG supports is run control, and this is sort of a generic term to describe a lot of different functionalities that are built into a chip. It's pretty much unlike the boundary scan commands, which are required by the JTAG spec. None of this is required. There's no standard. None of it's mandated. So everybody does it differently. But it's pretty consistent in what it allows. It allows you to read and write registers, memory, and usually I/O. And it allows you to control execution. So you can step through instructions. You can set breakpoints. You can do things like that. And this is really in there because if you are trying to debug software on a microcontroller and you're running on the absolute bare metal, nothing underneath it, no kernel, no hypervisor, nothing else there, and it doesn't work, you're either stuck or you can use this. And so I have never actually seen even the tiniest, most proprietary, barely supported little microcontroller with no software development environment. Every last one of them I've ever seen has at least some rudimentary form of this that allows you access to go in through JTAG and sort of poke at what's going on in the controller. So the second example we have here is slightly faster, and we're going to use some of these commands to just dump all of memory, and then we can analyze it. So Joe mentioned OpenOCD, and OpenOCD is really the tool that understands all these proprietary commands for doing the memory and the register accesses. And so it wraps these up in some generic functions, memory display words, so you can dump words out of memory. It's also got some optimized versions, so there's a mem2 array. If you've got a script, you can dump a whole array of memory into a variable. And they even have this dump image command that will let you take memory and write it to a binary file that you can look at. So what do? You've got memory, you just wrote it to a file. If you know what you're looking for, strings may be good enough. Binwalk will find some things for you. It will analyze these files. You'll see in the demo. It may take a while depending on how big your image is. Binwalk really does not appear to have been designed to run on hundreds of megabyte files very well.
So, and also Binwalk is really designed to be a file and firmware image analysis tool, but because of the fact that it knows what to look for, that knows the shape and structures and all the magic words for a huge number of file formats, it's really good at finding all these files that are located in memory too. And it's great because it's just one command, binwalk file name, and you get a list of what it thinks it finds inside this file.
So there's, I'm sure there are people here that are more familiar with memory forensics than we are. There's a whole bunch of existing tools, books, software packages. You can basically do anything you can do with any of these tools you can do on this image. You've just dumped raw physical memory. So you have all of it sitting in a file. You're free to do whatever you want with it.
So if you're ever in the need to do this on an x86 system, this volatility is a pretty cool tool for going through and understanding what's actually happening on a system based on a stale memory capture. So there's some pretty neat things you can grab that were stale in memory. It can reproduce. It can figure out things like a process list based on like kernel structures. So it's really good at taking all this data that you have out of memory and putting it backwards into what was actually happening on the system at the time. So, Volatility is the name of the tool set. It's open source. They've got a book that's pretty good. I've read.
This book was written by the guys who wrote Volatility.
So,
all right, so we've got a demo.
Do you want to explain what this layout is first?
Yeah, so
And then I'll start it over.
down in the far corner, I've got my OpenOCD. It's implemented as a server, and then you connect to it either through Telnet or through a script interface. So over here, I've got my Raspberry Pi running. I'm pinging. You can see it's running. I've connected through the Telnet interface, and you can see I can see a Raspberry Pi. I can tell it to halt. It's not pinging anything anymore. So I can read memory. So right now I'm apparently slow at typing. And we're going to read out some memory. I'm not going to, in this demo, display showing all of the memory on the device or trying to dump it all. It takes anywhere from 3 hours to about a day in the worst case, depending on the architecture and how fast things were running. So you can see me doing the dump image command here. I'm only going to dump a few KB here, and then I'm going to cheat and use the file that I dumped earlier than when I was recording this, because otherwise we would really be here all night. So you can see, wrote a file. I can start the Pi back up. It goes back to pinging things. I'm going to close down, and now here we're going to run bin walk on my previously dumped memory image, and you can see some things that are in there. Full disclosure, I did not actually even dump all of memory into that file because that still would have taken too long, and I was not that patient. So that memory file is, I think, 128 megs instead of all of memory. So you can see binwalk goes and finds some things. I kill it. I don't want to let it run forever. I'm just going to grep for some private key values and show you the private keys that were in memory at the time I dumped the image. So if you search for this nice block, it'll go and dump out all your private keys that were resident in memory. And you can see all the private, those were, I believe, from the SSHD server that was running at the time.
So just to reiterate the layout that we've got, what we've got is a system, in this case a Raspberry Pi.
Go to the next slide because there's a picture.
Oh,
yeah.
There we go.
So I've got a Pi, I've got it connected to my network, and then I've got, Joe's highlighting the JTAG device connected to it through some wires.
Yeah, you can
and that JTAG
see.
device is also running off screen to my workstation. And you can see my screen up above that I'm controlling things from.
And so when we run OpenOCD over here, or down here, OpenOCD is running on our host PC, our attack PC. It's running the server that is controlling the JTAG adapter, which is what is creating the TDI, TDO, TMS, TCK signals. There's this host client or client server interface, which is, so we have open up another window and access that client, that server as a client. So just so you're clear, all of these things, this is running on the Raspberry Pi. This is telnetting into the Raspberry Pi. These are both running on the local system using utilities to go and manipulate via JTAG. Good?
All right, so the cons, this is still slow. As I mentioned, this took, worst case, on one of the things I tried, it was like a day to dump all the physical memory. So it's still not good. If you know where you're looking in memory, it can be a little faster. I think out of the several dozen times I was trying to dump memory in order to generate this demo, the target resumed after dumping all of memory about once. So odds are you're going to bring the system down and it's not going to come back when you do this. So if you need to leave the system running after you're done with it, you probably do not want to do this. I'm pretty sure I mentioned this is not fast. And you need to be careful, especially on the Pi. The MMU got in the way a lot. So paging was enabled, and even when I tried to turn it off or use the functions that were supposed to bypass the page tables, they didn't. So it made it a little annoying to try and get just the physical memory instead of the whole 4 gig virtual address space.
Some of the things like the crashing and the MMU stuff, those tend to be like very device-specific issues that you'll encounter. Oftentimes, the manufacturer of the chip or of the board will have a recommended method of debugging the system. Sometimes it's a $20,000 debug system. Sometimes it's a $500 one, or sometimes it's a $50 like debug cable. Those generally work more reliably with a specific architecture than OpenOCD plus a generic JTAG adapter. But when you are getting a black box system, you don't know what's inside. You don't know what manufacturer you need to spend $20,000 with to get all this stuff to work right.
Even the proprietary stuff doesn't work that well.
Yeah, well, we don't want...
It's all got issues. So yeah, I was going to say, software is hard.
We don't want to reveal their IP, right?
Yeah. The pros, you don't need to understand a lot about this target, right? There are no target-specific commands here. It was just dump image. It gives you memory in a file. You can then go look through it. If you're looking for strings, you don't even need to know what the target architecture was particularly much. There's lots of existing tools for doing the analysis once you have the memory image. You can do inception type things very slowly if you want. And you'll still, you might not be able to take vacation for a week, but you'll have plenty of time to take your wife out for dinner and hopefully get off the hook for not spending any time with her.
Or you could just, have a beer lunch on a work day. So onward. So what was the first one? What architecture? That was a Beaglebone Black. So we did ARM on the Beaglebone Black. We did ARM v7 on the Beaglebone Black, ARM v6 on the Raspberry Pi. We tripped over the light. Now we're going to move on to MIPS because, it's JTAG. Who cares what architecture it is? When we boot up a system, the target here is actually a TP-Link router, like a home router, and it's very similar to most of the home routers that cost between $20 and $100 that you might find. When we boot up, we have a bootloader that actually does the work of loading the kernel. If we were able to go in there, we'd see some boot arguments that tell us how it starts up. What's great about boot arguments is if you can modify them, you can really exert some great control. It's really tough. You just put this 1 at the end. Who knows what that does? Single user mode. And who are you if you're the single user? Root. OK. Single character. Actually, this is 2 characters because you have to put a space and a 1. So 2 character, the 16-bit way to root. So you got to figure out a way to modify these boot arguments. This router that I had found, it had these boot arguments in the bootloader, U-boot, but if I modified them, it never took effect. What I discovered is that these boot arguments were actually statically coded in the kernel. So I got a dump of the kernel image, and I was able to look and find these boot arguments here in the kernel image, and I see all the way down to the end, mem equals 32 mem, and then a bunch of null terminated string characters. So really, all I need to do is modify this byte right here, or this hex, well, this word, these 2 bytes, these 16 bits right here, and I should be able to modify my boot arguments. So what we need to do is we need to set a breakpoint. We have to do something to halt the system because we got to tell it not to be doing anything while we're going and modifying memory. We wait till the kernel is loaded in memory. Most of these devices have the kernel in some sort of storage. Lots of the time it's compressed. So the first thing that happens is it boots up, it grabs the kernel from flash, it decompresses it into memory, right? Once it's loaded into memory, we halt. We have a kernel that's loaded in memory. We haven't started executing yet. We can patch the kernel at this point, and then we resume and let the kernel boot with its modified boot arguments, and we can get a root shell. So here's our layout. We've got the boot log. This is the serial console spitting stuff out. And I just restarted the system, and then it opens the OCD. In just a moment, I'll start it up. At some point.
Give it a minute.
Oh, yeah, this one goes through. Oh, yeah. So here I'm trying to log in. I don't know the login username or password or anything, but I'm stuck here. So what do? Eventually, I give up. And we go to OpenOCD. We'll start up OpenOCD. We have a config file for the target, and it starts up. It found our device. It tells us the ID code. Move that out of the way, and I'll go to Telnet. This is connecting to OpenOCD again. And I tell it to halt. It stopped. This device has a watchdog timer, which means if it sits idle for too long, it restarts. And so I halted it, and then it started again, and then I wasn't fast enough typing halt again, and it restarted again. But now I hit halt, and it's still really early. It's still in the bootloader, so it hasn't turned on the watchdog timer. So I can now go and look into memory. And this address I calculated based on where the kernel gets loaded and the offset, and I see the 324D, which is the last bit of 32M, and then null strings. The reason why it has a value there is because I've already booted once. It's already written that over. So I'm going to clear that out with a bunch of Fs so that I know that I'm going to write something. So we've got those Fs. As we load the kernel, it's going to write over those Fs with the kernel arguments, the boot arguments. I set up a watch point. WP is watch point. That basically halts the system anytime an address is accessed. A watch point on an address, the 4 means a 4-byte range. And I resume. And it halts. I'm going to remove the watch point and step over that instruction just to see what happens at that memory address, MEDW, MEDisplay word. So we've already written one character, but the rest haven't been written yet. Let's put the watch point back on, resume. We'll repeat this process until the entire value is written there, okay? So now that we know they're done writing what the kernel is decompressed into memory, we can go and modify that by, at this address, putting the 324D. Instead of terminating the string there, I'm going to put 2031, which is a space and a 1, right? My 16 bits that I need to add. I double check, make sure it wrote that properly, so I have the end of my string there. I remove the watch point and resume. Oops, remove the watch point. Double check, still there. Come on, remove watch point and resume. And we keep booting, and bam. Yay. So, and then, yeah, it's got the pound sign, so you know it's a root. But that's how we did it on this system. And yeah, so, woohoo. Any questions before we go on to the next root shell? No? OK. This is a photo of the diagram. This is the wireless router. I've popped the top off. Inside, there was a header. There was a 14-pin header. Actually, before I even bought the router, I looked up the FCC filings for that router and saw that it had a 14-pin spot. So I was pretty sure it had JTAG. I bought it. I soldered a header on, and I checked. And sure enough, it was JTAG. And there's a little JTAG adapter hooked up to my PC. What? So this is a TP-Link WR841N. And right now, this is hardware version 8. And right now, there's hardware version 9, which is a completely different CPU, completely different board, and a different version of the software. And there's no JTAG pins that I've found on that new one. But if you look hard enough, you should be able to find, what? Yeah, so actually I bought several of the old ones on eBay. But there's new routers popping up every day. So they're going to still have JTAG on them in the foreseeable future. This whole thing is really the same as it was 10 years ago using a open Linksys WRT54G. It's just a matter of what router is being manufactured today and which is the one that has the JTAG port and which one doesn't. So cons, this has to be done once at boot time. Single user mode means nothing's mounted and you have to do everything manually. The pros of this, though, is you can do after a kernel signature is checked. If you have some sort of secure boot going on, you finish your secure boot process, it checked the kernel image, and it's ready to go execute the kernel image. That's when you start modifying it, and it still thinks it's the same image because it checked the signature once and thought it was done. This doesn't depend on persistent storage or the root file system contents. You don't have to modify any flash or files to do this because you're doing it all in memory. Pros, rebooting doesn't take several days. I don't know what I meant by that. Probably because everything else takes several days and this one doesn't. So
No, this is getting better.
this is getting better.
The next one's actually even the next one was the fastest one.
Yeah, the next one?
Yeah. So if the system's already up and you don't want to reboot it or you're just too lazy to reach over and press the power button, you have full read and write access to all of physical memory, including kernel space. So patch it. Make the kernel do something else so that it doesn't get in your way. So Linux, formatting problem.
Uh-oh.
Oh, well. So Linux enforces file system ACLs through a whole bunch of system calls that eventually all run through this generic permission function in, I think it was nameic file.
Namei.c, yeah.
And down at the bottom, if you go far enough along through the code, I cut most of it out. At the end, if it doesn't pass, it returns this -e access value. But right above it, if it does pass, it returns a 0. So I would like to change that. I would like for it to always return this 0 value and give me access, regardless of who I'm running as. So we can go ahead and we can figure out where this is being loaded. I sort of cheated here. I looked at the symbol table from the device itself. You can always, if you have another one or you can build the kernel, you can always figure out. It's not too hard to get the symbol table for most of these. So we can see the address the symbol table's at. We can go decompile the code. Sorry, not decompile, disassemble the code. And you can come see right down here is right up at the top, we have our return function where we're popping everything off the stack and then doing the return. Down here, we have this move -13 into EAX, and then we jump to the return function. -13 happens to be the numeric value for eaccess. So this is where we're setting the permission denied return. We've got, I didn't show it on here because there wasn't really enough space, but we know what the address is for that value there over on the left. So we can go change it. So there's actually a couple ways you can go do this. Down at the bottom here, you can see this is one command in OpenOCD. We write a 0 to that memory address, change those 4 bytes to 0, and then the permission function will always say you have access. OpenOCD has a lot of overhead. There's a lot of stuff that it's doing implicitly when you type a halt or when you do a memory access. It will actually go through and walk the page table for you in order to figure out what memory address it's supposed to be writing when you do this. So there's a lot of stuff that goes on behind the scenes that you may not always actually want to do, and especially because we would like one of these to be reasonably fast. There are some alternatives. So there's a standard format for describing these JTAG sequences, right? So you can sort of see a sample over on the here. And it mostly consists of this SIR and SDR, which are shift instruction register and shift data register commands. And this is just an ASCII representation. There's also a binary version called XSVF. And this is just a way to describe the JTAG commands in a very low level, right? This is actually just saying shift these 8 bits into the data register. And there are a whole bunch of devices that can play these.
So for at DEF CON, we presented Savior Burst, which was a little implant that had JTAG pins on it, and it still almost works. But basically, it was a little AVR chip that we could program with an XSVF file, and you'd plug it in, and every time the system booted up, it would wait 20 seconds and then dump a payload, which would be an SVF file, a list of commands that would go and do something like patch a memory or something like that. So the idea would be it's a small device you can plug in and wouldn't be noticed on a board. And,
I was going to say there's libraries for AVR for all sorts of almost limitless possibilities for devices that can play back these files.
Yeah, if it's got GPIOs, there's code out there to do it.
So the downside is it takes a little more work to turn your one OpenOCD command into an SVF, but what you get out of it is a lot of portability, a lot more something that's a lot easier to reuse with different hardware. And you can make it quite a bit faster.
Ready?
So yeah. So okay, here we've got I've got a Galileo sitting over here, and I'm logging in as myself. I have a really secure password, and I do not have super user privileges at the moment, so I can't do things like read the shadow password file. So after I'm done proving I can't read the shadow password file, I'm going to go over here on the bottom corner and start up my OpenOCD server. I've got the config for the Quark file that Intel published. And so now here's the actual SVF I'm going to be running. It's just a list of instruction and data registers that I'm shifting in to implement the memory write command. So I'm actually loading up OpenOCD to go play back this file as well. It has SVF playback, so I don't have to hook up a different device to do this. So you can see we're connected to the Galileo, and now I'm just going to play this SVF file that goes and writes that word to memory. And when I come back over to my shell, I can read root files.
Yay.
So the downsides here, you actually have to understand a little bit of what's going on under the hood if you want to turn this into the SVF. You don't need to do that, but the upside is, we flipped past it. I think it was about, I don't want to wait through the whole thing. It says at the end how long it took. I think it was like 2 milliseconds. So compared to some of these other ones, this is actually fast. This is not kind of fast. This is not pretend fast. This just takes a couple milliseconds, and that's just the time it physically takes to shift all the several hundred bits through the JTAG adapter at a couple megahertz, and that's really about it. So there's very little overhead in the delivery for this one.
15.
And you have to actually try and find something that's in a fixed location in memory, because one of the other downsides of the SVF is it's not really meant for this, so there's no sort of intelligence. You can't make decisions in the SVF. You can just either continue or you can die, and those are your only choices. So you have to patch something in a fixed location in memory. The upside, as I've said several times, it's actually fast. So this one is nice. You can rerun it. You're not going to kill the target. You're not going to run into a whole lot of problems. It's pretty stable. It's quick. It's easy to use. You have a lot of options. And you can apply this, as you saw on the target, when it's running without really causing any problems.
Okay. What's neat about this one, too, is we did this on a Galileo, which is the x86 platform. I don't know if you guys know, tomorrow morning there's a workshop targeting the Raspberry Pi, doing this exact same thing on an ARM architecture. Like literally the exact same vulnerability, or not vulnerability, the exact same modification to ARM assembly codes and the same C source file. We've got 5 minutes. So.
Okay. I'll go quick.
And if you want to do that workshop, they have kits at the front desk, and you have to get a kit, and it has all the hardware in it. 6 minutes. Oh, 15.
15.
Oh, okay.
Oh, we got plenty of time then.
Oh, good. Yeah.
All right. So the last example, if your kernel's complicated or being patched a lot, and you don't want to have to figure out the ASLR randomization or anything else, you can go patch a process. So we borrowed this from one of the slot screamer exploits.
Well, actually, no. This is someone else contributed to
Okay.
Inception. So Inception
Okay,
is a tool. It started out as just FireWire DMA issues. Basically, it bypass lock screens. Slot Screamer is what I worked on last year, which was a way of doing it natively in PCI Express. Someone added a new feature to it, so instead of having to have a kernel-specific, mapping of how to modify the permissions, he did a generic one that just targets a user process, getty, or yeah.
Yeah. So we borrowed this, and it goes and it targets the options string in getty to change dash dash to dash f, and that basically results in the user being able to log in without using a password. So if we know where this is in memory, and oh hey look, if we read the file and look at it, we can figure out what offset this is from a page that when it's going to be loaded into memory. We can go and we can search through every page. Is there another slide that has this on there? Oh, there we go. So we can go and search through every page at that address, look for the string in memory. If we find that string, we go change it. And then when we try and log in, it should just let us log in. OpenOCD actually has some examples in Python, and they have a scripting interface. So this ended up being, I want to say, like a 12-line Python script of code that I wrote after I used their example to use the memory read and write functions. So this was really, really easy to implement. And if you go ahead, I think we've got the demo of this. So over here, I've got the Quark again. Turns out I don't remember the root password, just my user password. So we're going to start up the server again. And I wish I'd made that a little bigger. So I've got this script, and I'm telling it to start from address 2 billion and start searching for that target string in memory at the offset that we had on the previous page. So you can actually see down here on the bottom, the server's actually doing a whole bunch of memory reads. Oh, hey, it found it. We wrote that byte. It didn't work because, as it turns out, there's more than one getty process running on this system, and it patched the wrong one. So we'll run it again, and it'll go through. So searching. There we go. I actually, in the script, because I didn't want to just crash the system, I wanted to keep it running. I pause every few million reads and let it run for a few seconds just so it doesn't hang for too long. And we find, okay, we now patched the one and we can log in as root.
Yay.
Yay. So I was going to say, this is pretty much the same target setup we had before. The Galileo, which is the target system. I've got the serial cable to log into it, and then the USB. this ribbon cable right here is actually the JTAG wires going over to the Galileo, and then it's just Adafruit FT232H
Yeah.
based JTAG adapter running back to my desktop. So the downside is you actually need to know about a process running on the system and where you want to patch it in order to get you something useful. Because as we mentioned before, dumping all of memory to analyze it takes a really long time. This takes, you may have noticed I did not start from the beginning of memory because otherwise it would have taken too long. Having run this a few times previously to the recorded demo, it was taking like 5, 10, 15 minutes. So that's why after running into it in about the same location after several reboots, I just decided to start there so we didn't have to wait quite so long. The pros, you can do this on a running system. So this is not going to bring the system down. It takes a little longer, but it's still quite fast compared to some of the other options that take hours or days. And this is potentially a lot more resilient to software changes because if your kernel's being patched or updated frequently, this is only really going to change if your victim process changes. So we will, by this weekend, have the scripts that we ran here up on the GitHub repo. I did some horrible things to them to make the demos run a little faster, and I need to clean them up before I let anybody else see them at this point. So, I mean, the summary is really, right, the CPU is running software, but if you run the CPU, software doesn't really stand a chance, right? And JTAG can, because we can go in, we have access to I/O, we have access to the instructions you're executing, we have access to memory and register contents. If we have JTAG, we have root.
Yeah. So to add on to that, though, there are some chips out there that do lock out certain functionality of JTAG, whether they disable JTAG on production parts. That is feasible on lots of devices, but very rarely actually happens. Some devices have like tiered JTAG access, so you can actually lock them out of accessing certain memory regions. But again, that requires the software and the hardware manufacturer to both properly configure those features, which doesn't happen all the time.
Yeah, I was going to say a lot of times that doesn't happen because a lot of times the company making the chip that puts all those options into it is not the one selling, for example, say the router, and if the company building the router doesn't know or care, it doesn't get used.
Questions?
Questions?